Thank you, Frank. My name is David Byrne. I'm a principal consultant with TrustWave Spider Labs. I've been working in information security for about 15 years now. Long time ago, I actually founded the Denver OWASP chapter. I haven't been active very much lately, so I kind of feel guilty about that. But I've been involved in one way or the other with OWASP for a while. So this presentation is subtitled A Case Study in Deep Dive Pen Testing. And kind of the history behind this, I wanted to give a presentation about this topic after an engagement that was performed a couple of years ago with another colleague. And one of the things that we discovered during that engagement was a vulnerability in the Oracle E-Business Suite, which is this massive collection of business applications, just about everything that you can think of that Oracle makes. And the vulnerability was quite simple. If you had a cookie named either OA Developer or OA Diagnostic, and you set it to 1, it would enable effectively a hidden feature in the application. And among other things, you could, without any kind of authentication, obtain a list of all of the active sessions, including administrator sessions on the server. So all you had to do basically was wait until an administrator logged in. You can immediately hijack their session and start imitating that user. This is a very major piece of software from Oracle. It's one of their large products in their application division. This vulnerability, though, had been there for years and years and never discovered. And one of the reasons, at least that I've speculated, is that the application really hadn't had anyone take a deep look at it. It had surface pen testing, I'm sure, before, where scanners maybe had been run against it, but nothing that really looked at the core of it. The way that we had discovered it was using some of the techniques that I'll be talking about later in this presentation that I would describe as deep dive pen testing. This type of approach towards penetration testing definitely can be more time consuming, but it also is far more realistic for advanced threats, for attackers that are basically willing to invest some time into their specific target. Conversely, it can also save time on giant applications where with something like the e-business suite, there's no way that you're going to be able to do a thorough job of testing it. So if you don't choose your targets within the application well, you could easily come away with very few vulnerabilities, but that wouldn't be a realistic or an accurate representation of the application security. In one form or another, this type of approach requires that you have access to the software. It could be that you downloaded an evaluation copy from the vendor. Maybe you got a hold of the installation media. It could be that you had some limited access, either intentionally or through a vulnerability to the server, and you dumped the application directory. Basically, the idea is that once you have that installation media, or whatever the case is, once you have access to the software, you can start applying reverse engineering techniques to it during the pen test and come up with some very impressive results. Throughout the presentation, I'll be using a virtualized test bed, or rather showing examples from a virtualized test bed. The application is actually live too. If anyone's interested, there's a open Wi-Fi called ORA AppSec. And if you just go to ebsexample.com, port 8000, it'll let you download some of the scripts that I've used in the presentation and also interact with the application. Just try not to break it for everyone. It is not the best designed application, in my opinion, and so it could be easy to knock over. Don't do scanners, don't change passwords, things like that. So it didn't take me very long in preparing for this presentation to kind of regret my choice. And by then it was a little too late because the conference had already accepted my paper. This application is a mess. There's over 250,000 XML files, and that's just the files with XML as the extension. There's a lot of other files that are XML formatted with other extensions. There's almost 300,000 Java classes that are comprised, which make it by far the biggest application I've ever looked at. And even if you figure that there's only an average of, say, 20 lines per class, which is an underestimate, you're still talking about millions and millions of lines of source code that are represented in the application. Some applications that I test, I would say that there's a very gross lack of documentation. This app, there's tons and tons of documentation, but most of it's terrible. And if you work for Oracle, I apologize. I'm not trying to beat up on you. It's just I'm venting a little here after months of my own frustration. But there's some good things about it that make it ideal for a presentation, or not ideal, but make it suited. Oracle provides evaluation VMs that you can download from their website. When they're uncompressed, a single VM is 238 gigabytes. That's the one that's running. It uses file system compression, so that it's not quite that large on my disk. Setting these VMs up is rather complicated. I'm not going to go into that at all. I just want to focus on the penetration testing aspects. So when you start creating your virtualized environment for testing, regardless of whether it's an Oracle application or some other platform, if it's a large application, I have a few recommendations. One is that ext4 is a lot faster for this type of analysis than NTFS or HFS on the Mac. It's amazing what a difference it makes. However, Eclipse, I found, is much more stable in Windows. Again, and you're dealing with hundreds of thousands of classes, so this is beyond the normal type of behavior that Eclipse was probably designed for. The more RAM you have, the better. Of course, the solid-state drive is best. And I recommend the InstaSearch plugin for Eclipse. It basically indexes your code base and allows you to, within under a second usually, retrieve the results for simple text queries. So I'm going to be going through several analysis strategies that you can use when you're reverse engineering a web application like this and doing a deep pen test. The first one's very simple. Look at the database. The VM has a database server running on it. It's obviously Oracle. There's tons of applications that support it. So exploring the schema, looking at weak storage of sensitive data and default settings, things like that. So in this example, I connected to it with a tool called Toad. Just grabbed grabbed every column that has passwords in it, or password. This isn't obviously a very exhaustive analysis of the database, but we can get some results very easily. There's a lot of different tables that have password, but there's one in particular, or a couple in particular that I wanted to show. Come on. So this table with admin password, if we do a select all from it, you can see that the credentials are being stored in plain text with no kind of protection at all. Obviously, these are default passwords. Another table contains plain text passwords as well. So this is a very easy way that you can get some quick findings that are important as well for the client. To get an overall idea, though, of how the application is put together, the place that I always start is looking at the running processes. So, sorry about that. There's a lot of Linux processes that you'd probably recognize, but as we start, sorry, hang on a second, there's icons getting in the way where you guys can't see. As you get a little further down, what you'll find is that there are a lot of, most of the processes other than the Oracle database server are running in the u01/install/apps directory. So the next step would be to identify the content that's on there. We know what directory it's in, and this is just a quick one-line script that will basically look at all the files in that directory tree and count them based on the extensions. Apologies, this works a lot different on my other system here. So the largest source of, or the largest number of extensions are with, or files are with the class, which is to be expected since it's Java. It's a lot of XML files. As you can see, start going down the list. There's other formats, JSP, JS. You can recognize a lot of these or figure them out, but the problem is they get in the way. It's not something that's very easy to handle. So what we need is some way of organizing all of this. And there's several reasons. One is that when you're trying to find content, if you have gigabytes and gigabytes that you're processing, it's going to take too long for most engagements. So removing as many files as you can is ideal. It'll help speed things up. Identifying the files based on the extension, but also on the format, so using something like the file command. Emptying the media files, not necessarily deleting them, because sometimes it's useful to say, okay, well, my browser requested background.jpg, where is that on the web server? Because I know where some other files I'm interested in are in relation to that graphics file. But emptying it out will speed up recursive greps and things like that. Being able to identify open source files is also very useful because you don't really need to reverse engineer open source. If you want to see how something in Apache Commons works, you just go to Apache Commons and download the source code. There's quite a few classes, though, that in a project like this that are going to be from open source projects that you can exclude. And then finally, being able to do things like identify duplicate files and extract any archives. So there's going to be a lot of WAR files and ears and jars and whatnot. Being able to see what's inside of those and do text analysis against them is critical. So there's a lot of different ways you can do that. I wrote a script that I use on projects called extract.pl. It's a Perl script that basically takes care of the things I mentioned on the last slide, uses multi-threaded archive extraction. I have about 3 million hashes from public Maven repositories so that I can identify files that are open source and just exclude those from the analysis. And then it will basically sort everything out into a directory structure that's more usable. So this is basically what the script looks like. It's configurable based on the type of file. So for example, you can define tar archive, which is a pattern of what the file command will output. You can define a number of regular expressions that will match individual files. And then you can tell it what to do. So in this case, I just want to untar any tar files that are found. And it's quite a few different file formats and archive formats that it supports. So running this, it takes quite a while. It would take hours. I have a reasonably fast machine at home, but it still can take hours to run. It's an iterative process, like I mentioned before. It will move the jar files around, keeps track of which files it's touched so that it doesn't have to rescan anything. It will also list out the files that it doesn't know how to handle. So in this case, a lif file, there's quite a few of these. I have no idea what a lif file is. But with the path, you can go and take a look at the contents and manually check to see whether it's anything you need to be concerned about. So let's see, we can skip the rest of that. Once the files have all been extracted, the classes are one of the main targets that we're going to have for reverse engineering. But they're spread all over the place because there's going to be jar files and containers of other types that are throughout the application, not necessarily going to be organized very well. There's another script that I use called organized classes, and basically it uses a small Java application to extract the package name from the class file, and then sorts them into a proper directory structure, and also logs any duplicate classes, since handling duplicates is one of the more difficult things with something of this size, and oftentimes you end up just having to abandon them and hope it's nothing important. Once the files have been, or once the classes have been organized, you can see how many there were, 325,000 in this case. The next step is to decompile it. I use JDGUI. It's a pretty good tool. Some problems with it though. There's some counter, I'm guessing, will crash if you throw too much data at it. My suspicion is that it's something to do with a variable counter because it's not a specific number of classes, it's not a specific number of bytes. So you need to split up the classes, limiting the zip files that are created based on the number of bytes and the total number of classes. Once that's done, excuse me, Java decompiler is actually pretty fast. This is not sped up. This is actually how responsive it is once you've loaded a zip file. It will instantly decompile a specific class. This part is sped up. Unless you have a very fast processor, it'll take a little bit longer to generate a dump of all of the Java source code. And when you do, it organizes it into another zip file that's structured pretty much how you would expect based on package. Or actually, it's based on however you provided the organization. So once you have everything sort of organized and decompiled, there's a number of different strategies that you can take. My favorite is what I would describe as juicy targets. It's not very scientific, but after you've been penetration testing for a while, you kind of get a feeling for where vulnerabilities are more likely. So places that I like to look are files maybe with download or upload, some kind of diagnostic or debug tags in the name of them. Obviously simplification, but one advantage is that it can result in very rapid findings that are very significant. It might be a little more difficult for junior testers though, because it may not be as obvious to them where to look for things like this. And if you're doing any kind of thorough vulnerability assessment, it's completely inappropriate because there's no way that it's not a very methodical approach. It's more spot checking. So, for example, in the JSPs, JSPs that are included with the Oracle application, there's quite a few that have download in the name. BIS download is one in particular that I know because my research is vulnerable. In Eclipse, once you've loaded all of the results of your decompiling and everything, it has some very useful features. One of them is that you can open resource by name. So I can just type in BIS download, and it will, after it's been indexed, it'll let me open it up very quickly. In addition to opening up the JSP, the Oracle application server uses compiled JSPs. It's not actually looking at the text file. It's looking at classes that are pre-created and cached. So the name of this one, if you can read it, is the BS_BIS download.java. So it's basically the full representation of the JSP. It's also nice because you don't have to navigate throughout JSPs. So a lot of times if you look at a JSP, you'll see that there's an include that references another JSP, and you can have a whole series of these that make it rather difficult to read. When the JSP is compiled, all of those includes are put into a single class so that you don't have to really look around for the content that you want. So we can see the the HTTP servlet request variable, which is just the request that comes from the browser. There's a number of cases where it's using get parameter and storing these into variables. Another thing that's useful about Eclipse is that you can do refactoring on the fly. So I can refactor it. Sorry, I apologize. PowerPoint is being very erratic about when it decides to pause and when it decides to go forward. So you can rename these variables to something that's a little more useful that matches the purpose of the variable, and very similar if you've ever used something like IDA Pro, where you can rename pieces of data that will make it easier to track in the future. So there's a couple of vulnerabilities in this application, in this JSP page. One in particular that we're going to look for is, so thought it would be a lot easier to do a demonstration with recorded videos, but I'm thinking that may have been incorrect. So on this line right here, it's calling the get value method of local HTTP session. Now, if I was to try and open up the HTTP session, it wouldn't work, unfortunately, because when we discarded all of those open source projects, that included things like the HTTP session, which is part of a standard Java class. So it's hard to say exactly what get value is if you're not familiar with the application or with the framework. Google's our friend here, though. What we can do is go to look up just HTTP session get value. It'll pull up the Java docs on the right class, and what we see is that it's a method that basically just returns a variable in the session, a session data. The problem is that that is being called based on user-defined information. We don't really know what's in the session, though. And this is another thing that can be very useful when you're doing a reverse engineering techniques when you have a virtual machine running. I can go onto the virtual machine, I can find where the JSPs are stored, and create new content, basically. So I'm going to create a quick debug file that will basically just iterate through all of the session variables, recompile the JSPs, and I'll log in real quick just to give it a little more session data in the session. And when I request the debug page, it will give a full dump of the output. Wow. Okay, so these are all the different session variables. There's no way these should be accessible to a user. It's not uncommon at all to see sensitive data in here, for example, user's password or perhaps a database connection string. I've been recording this, and I was recording this in Burp. We can go grab the some of the variable names, and object key is the parameter that the JSP is using. All we have to do is paste that in into the repeater. So object key is whatever this button message, just some random session variable, and it returns the data. So this is something that, for example, cross-site scripting would be great for exploiting this. If you were targeting a specific user, you could start extracting information in their data in their session. You could also use it against your own session to look at, like I said, things like database connection strings. If you grep through the source code, you can see a number of cases where the application, the Oracle application, is putting values into the HTTP session that it really shouldn't be. I think it scrolled by the ones I wanted to show, but basically it's putting, here we go. Anyway, just take my word for it. It's it's putting some passwords and other information that it shouldn't be in there. So the next strategy that I would use is something I might call advanced grep. This is a simple script that I threw together. Basically, it just looks at a JSP or a series of JSPs, identifies where it is grabbing, where parameters are being pulled from the request. So, so basically user-defined information. And what we can do is, here, this video shows real quick a quick run. All right, so this is a simple output of the script. You can see what it's doing. This is a constant, so something is root param. It's grabbing from the request, the script is, and putting it into the root variable. Then later on down, we see that it's being dumped out without any kind of output validation. There's a lot of poor output validation in the Oracle framework here, but they actually check for some strings. So for example, you can't just throw a script tag in there or something like that. All that we're doing with this script is looking for cases where unvalidated input is being put into an existing script, because that makes it a lot easier to come up with an exploit string. So if we request this page, it's just some kind of category picker. We can pass root to it, just throw in something like ASDF, And in the source code, we can see what the output context is. This is pretty simple. We need to escape from a single quoted string and then from a function, and then we can write whatever JavaScript we want. So going back to the request, we'll escape out, put in an attack string, create a new function, and it's vulnerable to cross-site scripting, which is no surprise. So one thing that's interesting, though, the script isn't perfect. It misses a lot, but it doesn't have a very high false positive rate. And if you look, well, basically the script, here we go. If you see it, look at the very bottom, and of course it's covered up. Basically, there's about 150 different cases of cross-site scripting in the JSPs there. There's also static analysis tools that can be used. There's a lot of commercial products, some free open source products like Find Bugs. Of course, anything that's automated, there's certain advantages, but a lot of the tools aren't designed for mammoth applications, like in this case, several 100,000 classes. So it can require some very hefty computing resources. And also there's a lot of dead ends just because they're, the nature of false positives. With Find Bugs, you can get some information. So here, what I'm doing is basically inputting a classes.zip file, which is all the classes zipped up into one archive, and then providing it with all of the jars that are referenced so that it can basically resolve dependencies. And then the source directory so that it can show where in the source code it is. So it found a lot of security vulnerabilities. Some of these are real, some of them aren't. If we open up one of them, we can find it's in Git minifier, or excuse me, it's in minifier filter. I'm not sure exactly what that is, but we can open it up in Eclipse very easily. And it told us that it was a directory traversal. Now, one thing to keep in mind, it's going to be giving the line numbers based on what the class file reported, which once you've run it through JDGUI or any kind of decompiler, it's not the actual text line numbers, but it will put the line numbers from the jar or from the class file in the left column. So we can find where it reported the vulnerability. And here we go, it's opening a file using cache file name. Where does it get cache file name? It gets it from the request URI. That's a very insecure way of doing it because there's no validation here. So this is definitely a case of path traversal. The challenge, though, is how do we get to this? And this is one of the challenges with a lot of the types of analysis, where you might be able to find a vulnerability in the code, and I am certain that this is a example of path traversal. But actually being able to exploit it and discover how you call it can be very challenging. So if I open up the call hierarchy of Git minified bundle, it'll run for a while, and basically you'll see that it doesn't find anything. Now, that is a class that's used, but it's very, very difficult to track down how to access it. So sometimes you end up with dead ends like that just aren't worth pursuing. Another strategy is inside to outside, which I would kind of describe as reverse taint checking, where with taint checking, you're tracking data as it comes in from the user and seeing if it's ever properly validated. With reverse taint checking, which is that's not really a real term, but you're looking for key functions. So for example, it could be calls to a database, looking for SQL injection. It could be opening up new files, like in the last example, we could have looked for all the constructors to file that, and then tracing backwards. One advantage is that you can focus on very specific types of vulnerabilities. So if you're looking at all of the calls to JDBC handle, that's a very thorough way of checking for SQL injection. But on the other hand, like we saw in the last example, it can be very difficult to actually discover how the vulnerability should be exploited. So in this case, I'm just going to look for execute query. Now, it is being called execute query, of course, is just a common way of calling SQL, and not necessarily the best way because it's using just string as opposed to any kind of prepared statement. It's in the statement class, or rather the statement interface, which is normal. And if we open up the call hierarchy, which is a standard feature of Eclipse, it will list every method that calls that method. So it basically just will create a tree or a hierarchy, as the name implies. We can go in and open up each one individually, and in the first case, we can see here that it's pulling in something. It's using dynamic SQL, which is bad, but plan ID is also is defined as int, so there's no way that you can exploit that. It's bad practice, but not vulnerable. Going on to we can look for some more, and in this case, the method is calling, again, dynamic SQL. Table name, though, is just a string that it's coming in. Now, we don't know from this context how table name may have been validated earlier, but this is absolutely poor practice and could easily result in a vulnerability, a SQL injection vulnerability. In order to determine if it was actually exploitable, we'd have to track back through the call hierarchy and find where it was accessible from users. Reviewing log files is another technique that can be useful. So let's say that we have we've discovered sorry. Oh, these aren't movies. These are just screenshots. That's why it wasn't working. So let's say that we've gone to the application server and we found something called XDP XML query. Who knows what that is? If we request it, we just get a blank page. That doesn't necessarily mean that it's broken. It just means that something went wrong. If we connect into the VM, we can run just a quick command in the application server directories, looking for any files that have been modified within the last minute. By keeping it really tight in a narrow time frame, we can avoid getting a lot of false positives. So most of these are going to be some statistics and some, for our purposes, useless files. But there's two in particular. One is the access log. Now, we don't really need to look at that because the access log is just going to tell us what we requested. But the application log is going to be the most useful. And if we were to open it up, we could see that an exception was thrown when we requested that JSP. So if we were to, we could do basically like a tail-f and monitor that log while we're sending requests and end up getting a lot more information that way. The last analysis strategy is essentially taint checking. Being able to identify the external interfaces, trace the execution flow from where user input enters the system, and then identify how how vulnerabilities might result from that. This technique is much easier to exploit, kind of like the advanced grepping. It gives you something right off the bat that you can start to use. But there's a lot of dead ends because presumably not every user input is going to be vulnerable. And I had a video for this, but it got messed up, so that is all. Any questions? All right, thank you.